Hello class, welcome to this video on AP Statistics, Lesson 2.1, describing location in a distribution. So first thing we're going to be looking at is measuring the location with percentiles. So one way to describe the location of a value in a distribution is to tell what percent of observations are less than that particular value. And this is known as the percentile. So the p percentile of a distribution is the value with p% of observations less than or equal to it. And so let's look at an example. Let's say Jenny earned a score of 86 on her test, and this is the distribution below of test scores. So how did she perform relative to the rest of the class? So if she got an 86, we're looking for what percent of observations were less than or equal to her score of 86. So if we look at the data, what's bold are the scores that are 86 or below. The 86 is obviously her score on the test. We had someone score 85, 84, 83, so on and so forth below. So we count the number of observations here, and it's going to be 22 of the 25 test scores. So therefore, because 22 of the 25, 22 divided by, so in this case we have 22 divided by 25 times 100, that's going to lead to 88% of the scores are equal to or less than hers. So her score is at the 88th percentile. So keep in mind that we want to use the word at the 88th percentile. We don't want to use any other terminology other than that, because for the AP exam is very particular with wording. So here we want to make sure that we say that her score is at the 88th percentile. Let's go ahead and take a look at a new type of graph known as the ogive. So the ogive is basically, a term for a cumulative relative frequency graph. So what this graph does is it's basically like a line graph. It's a sequence of lines here, line segments that connects each dot. And on the y-axis you have your cumulative percent, otherwise known as a cumulative relative frequency. So what is that and how do we find it? That's what we're going to find out now. So let's say we have the following distribution of ages of the first 44 presidents when they were inaugurated. We got their frequencies, and so what we want to do is we want to convert them to relative frequencies. So the first thing we want to do is we want to take the total here. The total here is 44, and so the relative frequency for the first observation is going to be 2 out of 44 times 100. That's going to be 4.5%. And we do that for the rest of the observations, the rest of the frequencies, to get the relative frequency. Now next is the cumulative frequency. So the cumulative frequency is the frequency that basically is built up over time. So for example, the cumulative frequency for the first set of observations is 2, because that's what we start out. We start out with a frequency of 2, and then as we continue, we build our frequencies, right? So then 2 plus 7 is 9, so we accumulate over time. And then 9 plus 13 is 22. 22 plus 12 is 34, and so on and so forth. So we add the frequencies as we go down, and that's how we get our cumulative frequency. So here we got the 2 and the 9. Again, we got the 2 plus 7 equals 9. And then 9 plus 13 equals 22, so on and so forth. So that's called the cumulative frequency. So now the cumulative relative frequency is taking the cumulative frequency and then dividing it by the total. The total is 44, if you remember, 44 presidents here, the first 44. So we got 2 divided by 44 times 100, convert all those to percents as we work our way down. So this right here should say, okay, so I wanted to make a correction to the percentages. So I went ahead and made the correction. So cumulative relative frequency, again, 9 divided by 44 times 100 is 22.5%, and so on and so forth, right? So once we get the cumulative relative frequencies, we're going to graph them. So this is going to go on the y-axis, and on the x-axis is the age, right? So notice that the first, and also notice that even though the first cumulative frequency is 2, we always start out at 0, okay? So here for 40, the cumulative frequency is 0 there. But once we get to 44, the cumulative frequency goes to 2. So at 40, notice that we got a value of 0. Then once we get to 40, 44, 45, that's when we get the value of 2, right? So that's what this value refers to. So we got this, so this is that first value. Then we get to 9 when we get to the 50 mark, right? And then 3, and so on. Okay, so those are well, in terms of percents. So let me reiterate that. So we have 4.5% for the first one, then 22.5%, and then 50%, right? So that's what this refers to. And this is your ogive. So your cumulative relative frequency percent graph, right? So this is how it looks like. Now, we are going to use this graph in order to find percentiles for different, different percentiles. So for example, if we look at, let's look at the next, so let's just kind of zoom in on that graph and focus on it. How do we use that graph to determine what the first quartile is, the third quartile is, and the median? Well, remember in the previous lesson, we looked at quartiles. So that was lesson 1.3. So the first quartile is the 25th percentile. So this here refers to 25%, right? And this refers to 50%, and this refers to 75%. And so to find the first quartile, you need to figure out what the 25th percentile is, cumulative, right? So in this case, the 25th percentile is going to be like around here. This is about 25, right? And so you can find your point from there. And then your age is going to be whatever that age is on the x-axis is going to be your 25th percentile. Well, it's going to be located at the 25th percentile. Okay, so let's look at the first quartile. So the first quartile is at 25th percentile. That's at an age around 51. Then the median is the 50th percentile. So that's going to be located at an age of around 55 for the age and inauguration. Then the third quartile is around 75th percentile. That's going to be located at approximately an age of 60, 59 to 60. All right, and that's how you locate various percentiles using the ogive. All right, so now we're going to measure the position. We're going to talk about z-scores. So the first measure of position was the percentile or the quartiles, because quartiles are a different form of percentile, right? Now the next measure position is the z-score. And so you may have seen z-scores before. So z-score tells you how many standard deviations from the mean an observation falls and in what direction. So it's going to be a positive quantity, it could be negative, or it could be 0. So if it's positive, that indicates that it's in the direction above the mean, and then negative is in the direction below the mean. Okay, so let's calculate the formula to convert to a z-score. So if x is your value, your data value, then you subtract the mean from the data value and you divide by the standard deviation. Remember that the symbol for the population mean is mu, so this is the symbol for population mean. And this is the symbol for the population standard deviation. Okay, so that's the symbolic form of what we have on the left side. So a standardized score is often called a z-score for short. All right, so remember that a z-score should not be interpreted as a distance away from the mean. It's basically just a number of standard deviations. So it's not like a distance, it's a number of standard deviations from the mean. So you want to be very careful, especially on the AP exam, when you interpret things like z-scores. And then you have to indicate the direction, whether it's above the mean or below the mean. So it's, for example, if you have a z-score of 2.1, right, or negative 2.1, then you would say that the data value is 2.1 standard deviations below the mean, right? So that's how you would kind of describe that. So positive z-scores, again, are above the mean. Negative z-scores indicate observations below the mean. Okay, so let's look at an example. So let's go back to Jenny. Jenny earned a score of 86 on her test. The class mean is 80 and the standard deviation is 6.07. Find and interpret her standardized score. So we're going to calculate. Now we know how to calculate the mean from the previous lesson. We know how to calculate standard deviation, and those are, the standard deviation is, can be a pain to calculate. So I went ahead and gave it to you here. However, if they don't give it to you, you're able to calculate it either by hand or on the calculator. So here we go. Interpret her standardized score. So we know that the z-score is the value minus the mean on the numerator. So we got 86 minus 80. Her value is 86. The mean is 80 divided by the standard deviation. And you want to round this to about 2 decimal places. So notice that we round this to 2 decimals. And there's a reason for this. Whenever we use the z table, that's going to be a table that's in 2 decimal places. And so generally, we want to round it to about a couple decimals. So here we got 0.99. So her score is 0.99 standard deviations greater than, because it's positive, or you can say above the mean, right? Same thing. Greater than the class mean of 80. All right, pretty straightforward, nothing crazy here. So let's look at another example. Derek is 66 inches tall. We want to see his measure of position among 16-year-old boy heights. And they have a mean of 68 inches with a standard deviation of 1.5 inches. You can see that Derek is below average as far as his height, right? So we know that his z-score is going to be negative, and that indicates he's below average as far as the height is concerned. So we're going to find and interpret his height. So again, plugging into the z-score formula, we got his height is 66 minus the mean of 68 divided by the standard deviation of 1.5, and we get negative 1.33, which means that his height is 1.33 standard deviations less than or below the class mean of 68. Okay, so we've done an example where it's positive z-score, and we've done an example where it's a negative z-score. And this gives you your relative position among your classmates, right? In this case, right? Or in this case, the 16-year-old boys. So this gives him a sense of position. Where is he located in the distribution overall, right? So that gives you that sense of position, just like percentile does. All right, so now we're going to look at transforming data. So transforming converts the original observations from original units of measurements to another scale. Kind of like the z-score. The z-score transforms something from the original to a scale that's known as a z-scale, right? So we have to know how transformations work. So transformations can affect shape, center, and spread, depending on the transformation. So for example, let's say you want to convert feet to inches or Celsius to Fahrenheit. Well, then you need to include a transformation in order to get the data to be converted, right? So another example would be what we just did with the z-score. We converted Jenny's score, or Derek's height, in inches into a z-score. Remember that z-scores are unitless, so z-scores have no units. So we converted something that had units to something that did not have units. So that's a transformation. So each data value will be subtracted by the mean, and then difference is divided by the standard deviation. So this is what we do for the z-score, right? So how would the data point be transformed? Well, we'd have to subtract it by the mean, and then we'd have to divide by the standard deviation. Again, the formula for the z-score, right? X minus mu divided by the sigma. Okay, x minus mean divided by standard deviation. That's going to transform to the z-score. So transforming converts the original observations, like we said, to another scale. So what are some transformations that we can do? Well, we can look at adding or subtracting a constant. So if we add the same number, in this case a positive number, a, or we subtract a from each of the observations, that is a form of transformation, right? So let's assume that we're adding or subtracting a constant. So what happens? Well, first off, if you add or subtract the same number from each data point, what does that do to the center, location, things like that, right? So first off, it doesn't change the measure of variability. So the range is unaffected, the IQR is not affected, the standard deviation is not affected, right? However, the mean, the five number summary, the percentiles will be affected, right? So if I add a certain value to it, then it will add the same amount or subtract the same amount to the measure of center. All right, so for example, if the average of a set of data is 5 and I added, and let's say I got the data, I'm just going to make up the data, and let's say I added 5 to each, or added 2 to each data point, right? Well, then that's going to convert the mean from 5 to 5 plus 2, right? So whatever we add or subtract from each data point is going to affect the mean by that same amount, okay? However, it will not affect the range, right? Or the standard deviation. It will only affect the mean, okay? So in this same example, let's say that the highest data point was 10. Well, then in this case, the range is 10 minus 1, or 9, and that's unaffected. So that will not be affected at all, even if I added 2 to each data point. In addition, it does not change the shape of the distribution. So if it's symmetric to start out with, it's not going to change it to something, a different symmetry, okay? So it's not going to change shape. So what happens if we multiply or divide? We're going to look at that later. Okay, so let's look at that now. So multiplication or division by a constant. So if we multiply or divide by the same number for each observation, well, first off, it's going to multiply the mean or the whatever measure of center we're using by that same amount, okay? So again, if the mean is x bar equals 5, and we multiply each data point by, for example, times 3, well, then it's going to affect the mean by that same amount. So then it's going to multiply that by 3, right? Or if we divide by the same number, it's going to divide the mean by the same number. It will also multiply or divide the measure of variability. So it will affect the range, okay? So for example, if the range here is 9, then the new range is going to be 9 times 3. Because now we have 1 times 3 is 3, and then 10 times 3 is 30, and then 30 minus 3 is 27. So it affected the range by a factor of 3. Okay? It does not change the shape, however. So it will affect the two measures, but it will not affect the shape. Okay, so let's look at an example. So let's look at the metric system. Soon after the metric system was introduced in Australia, a group of students was asked to guess the width of their classroom to the nearest meter. All right, so so we're going to track down their guesses. So they were asked to guess the width of their classroom in meters. And then we're going to track, each of these observations, what their guesses were. The actual width was 13 meters, and so what we're going to do is we're going to examine the errors in the distribution, right? So what was the error in their guess? So we take their guess minus 13, and that's the error. Okay, so this is the original guessing distribution, the original data, and then we want to analyze the guess date, or the error, right? So what happens if we subtract 13 from each of these guesses in this distribution, right? If I do minus 13 to all of these data points, what will happen to the shape? Well, first off, since we're subtracting, if we're doing a transformation by a constant, then it's not going to affect the shape. So the shape is going to be the same. And here, in this case, the shape is going to be skewed to the right. All right, you can see that the longer tail is on the right side. So it's going to be unaffected. Now for the mean and median, it's going to subtract the 13 from the mean and 13 from the median, right? So in this case, the mean, they mentioned that the mean is 16.02, right? So we're going to subtract 13 from that, and that'll give us our mean, 3.02. It's going to also affect the median, right? So it's going to be minus 13, so the median is going to be 2. Okay? So that's how it's going to affect mean and median. Now the standard deviation and the interquartile range, those will, if you recall, those will actually be unaffected, right? So if we're adding or subtracting the same number, they will be unaffected, so they will remain the same value. Okay. So now let's take a look at the entire number summary for the the error distribution. Okay, so we have the error in their guesses on the bottom graph, and then we have the original data on the top. And then this is the 5-number summary, or not the 5-number summary, this is the generic number summary for that distribution of errors. Okay, so we said that this one was subtracted by 13, this one subtracted by 13. Notice how it affects the quartiles. The quartiles also get affected, right? So they also get subtracted by 13. Obviously, the maximum number is going to be subtracted by 13, so is the minimum number. So you have to know which ones get affected, right? The standard deviation is left unaffected, and so are the interquartile range, and so is the range, right? We mentioned that earlier, the range is unaffected. Okay, so make sure that you know how the data is transformed from one to the other for each of these numbers in the number summary. Okay, so now let's look at multiplication and division. So now let's say the students are having difficulty with the metric system. So what we want to do is that we want to convert the data to feet because they're used to using feet, right, instead of meters. So it says it may not be helpful to tell them that their guesses tended to be about 2 meters too large. They had really bad guesses because they were just introduced to the metric system. So they want to convert to feet. So in order to convert from meters to feet, remember we have to multiply the data values by 3.28. So we're going to multiply by the same number, right? So we're going to convert their errors to 3.28. So what shape does the distribution of error have now? Okay, well, so first off, so remember that since we're multiplying by the same number, 3.28 in this example, that's not going to affect the shape. So the shape is going to remain the same. Here in this case is going to be skewed to the right. So the shape is unaffected. We know that. Now the median is going to be affected by the multiplication. So the median, we're going to need to multiply the median by 3.28. So we're going to need to multiply this guy by 3.28. So that's going to be 6.56 feet. All right. That will also affect the average. So that will also affect the x bar, right? So we would also have to multiply that by 3.28. Okay, so just keep that in mind. The interquartile range will also be affected. So it's also going to be affected by this. So we're going to need to multiply by 3.28. So will the standard deviation, right? So that will be affected as well. And so measures of variability are affected. So let's go ahead and zoom into the graph and show you the error distributions. So we have the error in meters, and then we have the error in feet. So we converted those. So notice that the shapes are the same. They're both skewed to the right. However, the x bar got transformed, so we got to multiply that. We got to multiply the median, right? So we got to multiply that. So times IQR times range times maximum. Obviously, we got to multiply. Third quartile, first quartile, we got to multiply by the same number. So all of these get affected. So when we multiply or divide by the same number, it's going to affect every single observation, every single number statistic here. Okay. All right. So now we're just going to kind of summarize the transformations, the z-scores here. So if you look at so we're gonna do what we did, but we're gonna do it with z-scores. Remember that there's a couple of transformations that take place, right? If I take a data value, I need to do this transformation first, and then this transformation second, right? So I need to subtract it from the mean, that's a transformation. Then I need to divide by a standard deviation, that's a second transformation. So we're gonna do a step-by-step transformation and see how that affects the shape, center, and spread. So remember, when you subtract the same number, we're going to say that the mean is A in this example, and then the standard deviation is B, okay? So in this example, that's what that refers to. So if we subtract A from each of the data values, how's that going to affect the shape? Well, remember, if I subtract the same number, it's not going to affect shape. So if I divide by the same number, it doesn't affect shape. If I divide by the same number, it doesn't affect shape. And so overall, the shape is not going to be affected. Now, if I subtract the same number, what is that going to do to the spread? Well, that's going to subtract the same number from the spread. If I divide by a number, that's going to divide the center by that by that number. So in this case, if I subtract a, that's going to happen to the mean. The mean is going to be smaller if I subtract a. And then if I divide by b, then that's going to affect the x minus a, right? That's going to obviously change that. We're going to divide that by b. Okay, so it's going to do that to each of the data values. So overall, it's going to subtract, each data value is going to be subtracted from x, right? It's going to subtract the constant and then divide by b. So that's going to happen to each of the statistics, right? So overall, if we look at the spread, well, it doesn't change the measure of variability. So the spread is not affected by subtracting or adding. The spread is affected by multiplication or division. So it's going to obviously affect that. However, and then so overall, it's going to affect the spread. So hopefully this kind of makes sense. It kind of breaks it into the two different transformations and then the overall effect, right? So this is important to realize when we do transformations and how it affects distributions. So it's definitely important for you to know this. All right, guys, that's going to do it for the lesson. I hope you found this informative. And as usual, I'll see you in the next one.